You are looking for Science2A task for U4L15. The do now, I want to use that projectile motion FET one more time. I know you're probably getting sick of it, but open up that same FET, and then there are instructions on a quiz. That's the next link over right here. It's just U4L15 do now. Again, this is not graded. It's just some questions that we'll review together. There are 4 questions that you need to answer, and the instructions are also in the questions of what you should do with the projectile FET. And again, let's take 8 minutes to work through this and see how we go from there. I'll be here listening if something isn't working, if you need help, but otherwise you got 8 minutes to work on task number 1, the do now. Go for it. All right, looks like the last few people have managed to submit it. Guys, have this is good to see that on Canvas quizzes, if I ask open-ended questions, I can't see your answers when I look at the statistics. It just shows me how many people have answered. Like for multiple choice, it gives you breakdown, but for open response, it doesn't. So I might have to use Google Forms from this point forward because I think I have to go through the gradebook to see results. So then let's just review this together. If I look at each question. So who got the first one? Did you notice, did they land in the same place when you fired the 2 projectiles at the 2 different angles for the first question?
No.
Any ideas why?
Because like the height elevation of the cannon.
Yep. And so this kind of shows, I don't know if I was tired or if I just wasn't thinking, but when I first was reading the chapter and was like, oh, that's cool, I immediately turned on the simulator and was like, I want to try this, and I'm firing from 2 different angles and they're not landing in the same place. And I'm like, what the heck? Like, did they make this app wrong? And I didn't realize that, yeah, the cannon's 10 meters off the ground. It has to be level with the ground. That's one of the requirements for this. So you have to be firing from that actual horizontal spot. So what angles did you use to hit the guy standing below the cannon?
-40 and positive like 75 or something. Like
Most people agree with that? Do you get like -40 and 75? And again, those don't add up to 90 in any way. And that's because, again, the cannon's at elevation. We actually have to aim below the horizontal to do that. Did anyone get why they have the statue of David down there? Why did they choose that of all things?
I said he looks cool. That's why.
I said because he's a height reference.
Could be that. Mm-hmm. Though, again, has anyone ever seen the David? Anyone been to Florence? No?
But he's really tall.
The statue's enormous. Yeah, it's probably 3 times taller than a normal human. It's really, really big. So it's a statue of David. Does anyone know the story of David and what David's famous for in the Bible?
David fought the Goliath.
He fought the Goliath. Does anyone know what he fought the Goliath with?
A sling.
Yes, he threw a projectile at Goliath and took out one of his eyes. So I think that's why they have him down there, is because he used a sling, which is technically a projectile for throwing. So I think it's the programmers being a little nerdy, if anything, but kind of funny. All right, the last question. When you applied drag, did the projectiles, when you fired it at 30 and 60, did they land in the same place?
No.
Why not? What does drag do to...
Air drag, right?
Yeah,
Like,
what does it do to altitude and to range?
It slows it. It makes both of them less.
Yeah, but not equally so, right? You would think that, okay, if drag's going to act on altitude and range, all the time, then maybe it'll slow them both down the same way, but it doesn't. It's sort of a unique combination of how that works, and so it throws that off. So again, that little adding up to 90 thing is a cool demonstration, but it's in an ideal situation. It's not really that realistic. You'd have to have no drag and be firing from the horizontal to make that true. All right, and that's sort of the gist of what we were covering in our previous lesson. So before we dive into new content, I wanted to give you a chance to ask questions about the homework. Was there anything from chapter 5, page 116, questions 21, 23, 24, and 25 that you wanted to look over, or anything you were confused by or left blank? All right, looks like we're feeling good. And just, I know it's sort of weird that I keep asking you to keep submitting your same digital notebook, but it's just convenient in the speed grader because I can literally click the link you submit and it just brings the notebook right up in the grading mechanism, and I can just grade things really quickly. So if you have not submitted your homework questions, please do so as soon as you can. Okay, I want to do, again, just another short lecture to review the last part of chapter 5.12. So I'll go through some slides here, and I'm going to try using Poll Everywhere on your phones. Have you guys used Poll Everywhere in any of your other classes? Okay, this is my first time using it integrated into Google Slides. I discovered an app that lets you integrate it, so we'll give it a try. But again, like before, feel free to take notes in your digital notebook or on paper if you want. I have posted, again, a recording of me going through these same slides that you can watch later if you want to as well. But let's talk about, this is the last section of chapter 5, all about what's called elliptical orbits. And I think the bigger part of this is escape velocity. And why, again, you've often heard that term of what goes up must come down. But technically, if you have reached escape velocity, like this dad here throwing his baby, you would not want to do that because the baby then would not come down. It would just continue to travel into space. Okay, so this is my first time trying this. First question I'd like to ask you is a little review question. What are satellites? You've got 4 options there, A, B, C, D. Take some time to read those over, and then you can respond if you just want to open a new tab on your computer or whip out your phone and go to polev.com/hatesci2. Or you can text hatesci2 to 223333 and then text the letter for your answer, and it should submit it. And as far as I know, it'll update on the screen when you submit your answers. So go ahead and give it a try. It's my first time using this, and let's see if it works. This is nifty, but it doesn't allow me to see the total number of respondents, and also there's no way to like hide the responses, which is normally kind of a more fun way to do it. But it looks like we are kind of torn here between whether they're the communication machines we launched into space or whether there are any projectile moving fast enough to fall continuously around Earth. So who wants to hop in? What do we think? What are satellites? Again, we're speaking scientifically here.
I think satellites are anything that, I mean, we often refer to satellites as like communication machines, but I think they're anything that orbits around the Earth.
Yes, the more correct answer is indeed C. We call, there's a certain image that comes to mind when you hear that word satellite because, yes, we use them so much for technology stuff, and we're used to seeing those, kind of the little solar panels floating around. But they're called satellites because they're launched into space to rotate around our planet, and that's it. So it could be anything. We could fire a rock. The moon is technically a satellite. So it's just good to know the scientific use of that. So. Cool. All right, numbers are jumping everywhere. So it looks like you can change your answers as well. That's a good tool to use. All right. So how do I move on to the next slide then? I guess I have to do this. There we go. Yep. So a satellite, again, just remembers any object moving fast enough to continuously fall around the planet. And we learned yesterday that the minimum required speed to achieve that would be something around 8 kilometers per second, because that sort of matches the curvature of the Earth, even though in reality the Earth isn't perfectly round. So the next part of this chapter is then, well, what happens if you're going at a greater speed, right? What if you're able to achieve, a projectile achieves more than 8 kilometers per second? And if you're slightly above that, you're going to end up in what's called an elliptical orbit. And this just means that you're orbiting in an ellipse, which is basically just a big wide circle that has, they say, 2 foci, which is essentially meaning 2 focus points. And in this situation, it's going to be a planet or a body of some kind that has gravitational force acting on it and whipping it around. But you can draw an ellipse like this. You could get 2 tacks or something like that, stick them into paper, and then use string or floss between them, make it taut using a pencil, and then just draw in a circular motion. That's what you would end up with. It's sort of a wider looking circle. But when you start to get satellites orbiting in this way, where it's an elliptical orbit rather than a circular orbit, you get to see some interesting behaviors. And so that's the next question I want to ask you. Just take your best guess on this. How does elliptical orbit affect the speed of the satellite as it travels? Is there no effect? Speed of the satellite is consistent, does not change. That's option A. B, it goes faster as it approaches and passes the focus and slower as it moves away from the focus. C, it goes faster when relatively straight and slower when turning. So you can kind of see there's that oval shape. Or vice versa, it goes slower when it's a relatively straight path and faster when it's doing those sharper turns. Take your best guess. All right, looks like most of us are piling on to option C. Anyone have some insights into this?
I feel like I've always heard when like astronomers are talking, they talk about like a body can be thrown around something and then exit the orbit. So I feel like when it's on the straightaway, it can speed up and just fly away.
Yep, but on that straightaway, it has just come around whatever sort of focus or planet or star that it was, right? And yeah, they often call this like a slingshot. This is actually what they use to get satellites going a little faster. Is they call it slingshotting around something, like the moon or Jupiter is often used, where it'll enter into its gravity and start to orbit really fast and then kind of shoot off. And so in reality, the correct answer is actually B. It tends to go faster as it approaches and passes the focus, right? As Ed was saying, that's sort of the slingshot moment. And then but if the body has a strong enough gravitational force, it'll actually start to pull it back. So it slows down as it gets further out and then comes back in. So what does that look like visually? I made another slide here to hopefully try to clarify this a little bit. So again, this is assuming that we are 150 kilometers above Earth in space, right? That there's no drag, there's no gases present. If you're in an elliptical orbit, then the satellite is going to move faster as it approaches and passes the planet or the star. So you can kind of see that right here. That's that faster motion happening here. And then that's sort of the slingshot, right? It's going to go, and then as it gets further and further out, it's going to slow down as it's sort of slowly dragged back towards this center of focus here. That's the gravity acting on it, kind of bringing it back in. And so you can think of the moon rotating this way around the Earth. In reality, the moon does this. The moon has what's called a perigee, where it's a little bit closer to the Earth, and an apogee, where it's a little bit further away. Again, I wouldn't worry about these vocab words. They're just interesting to know, but I don't think it's anything we would quiz you on. And then Earth also does the same thing around the sun. We have a moment where we're a little bit closer, called the perihelion, and I think this is the aphelion, or aphelion. I'm not sure how that's pronounced. What's sort of counterintuitive is, does anyone know what season it tends to be when Earth is in the perihelion, when we're closest to the sun? Do you think it's fall, winter, spring, or summer?
Winter.
Yeah. A lot of people think it must be summer, right? Because we're closer to the sun, it must get hotter. But in reality, it's typically winter time. I don't think it's 100%, but winter and summer are actually more due to Earth's tilt towards the sun, not necessarily the distance between the Earth and the sun. So kind of interesting little tidbit there. Okay, so that's what we call an elliptical orbit. And again, there's no second focus. That's what kind of throws me off here, is that when they're describing the elliptical orbit, there's two foci, right? So I'm not entirely sure exactly how that's working, other than that just the gravitational force, I think, from whatever bodies that it's rotating around is strong enough to still bring the projectile back towards itself. Okay. So last question to ask you using this, and this is going to be an open-ended question, so I just want to see what this looks like. What is geosynchronous orbit? Take your best guess. Try to break that word down. What do you think geo and synchronous mean? And again, not really looking for, I don't expect you to have any prior knowledge about this, so just take your best guess. And there's nothing I can do to stop you from hopping on Google and looking it up too, but I think it's more fun to guess and see what other people think. All right, I got 4 ideas. I want to hear from at least a few more of you. More than half the class. There's 9 of us attending.
I turned mine in. I don't.
Oh, okay. I wonder if it's not updating or something. All right, these are good ideas, though. I like this. Maybe the moon is orbiting around the Earth, synchronized with the Earth moving around the sun. Yeah, you've got 2 rotations going on there. I don't know how synchronized they are. There is something interesting about the moon, which I'll get at. Orbit where the projectile travels at the same speed as the Earth travels. So I got to clarify what's meant by the same speed. We'll figure that out. Orbit where 2 planets are orbiting each other in an equal way. Multiple things are orbiting the same way. So you're getting at this idea of synchronous being the same, right? Being timed in some way, and geo having to do with Earth. Little tidbit about the moon. This doesn't exactly correspond to geosynchronous orbit, but does anyone know, as the moon rotates around Earth, there is a little bit of a matching in that. Do you get to see different sides of the moon, or are we always seeing the exact same side of the moon?
I only see the one side of the moon.
Yeah, that's why you often hear this thing, the dark side of the moon, because it's never really been seen before from Earth. It's sort of an interesting thing that, yeah, the rotations of the way the moon rotates around our planet and rotates itself, it's always facing us with the same side, which is kind of crazy. Think about the timing required for that. But that's not what we call geosynchronous orbit. What geosynchronous orbit is getting at, these are all good guesses, and I think some of you are getting at this. You're just having trouble sort of explaining or stating it in a clear way. It's when you have a satellite that has its timing just right to float over one part of our planet. So here's what you have to understand about that. Satellites rotate around Earth at different distances, right? And that makes a difference in terms of how many times they make a rotation around our planet in a given amount of time, right? So satellites orbiting really close to Earth, they're experiencing just as much gravity as we are down here. And so they've got to be moving pretty fast. So most of these satellites here, you can see how close they are to our planet rotating around. That's called a polar orbit. They are going to circle the Earth every 90 minutes, right? Pretty clear that they're doing like the 18,000 kilometers per second. They're moving really, really fast. But if we can get a satellite to orbit Earth at a much greater distance, see how this one's much farther away from the surface of the planet, then it could have a slightly slower horizontal speed, right? Because there is a little bit less gravity, right? It has to be a pretty big distance, but then you could reduce the gravitational effect of planet Earth on that satellite and allow it to slow down. And in fact, you are able to get some satellites far enough away, specifically 5.5 Earth radii away, which is equivalent to about 22,000 miles. So that's a long way from the surface of the Earth. But satellites at that distance, they are able to stay in orbit with a horizontal speed that makes them rotate our planet every 24 hours. And as you guys probably know, Earth rotates on its axis every 24 hours. So it's basically matching that. And so those satellites, if everything's set up correctly, can literally float over a single point on the planet permanently. Imagine having a satellite that is basically right above your head, 22,000 miles up and away, but then it's always there. Now, I don't exactly know how that works in terms of Earth's tilt. I think there is some adjustment that has to be made because the Earth is constantly tilting back and forth and wobbling on its axis. But otherwise, we have a lot of satellites that are doing this. Most satellite TV satellites, as well as I think a lot of cellular phones and things like that. If you've seen people with their like satellite TV dish on their roof, it's always pointing at one spot, and that's the spot where the satellite is, but it's 22,000 miles away. So that's what's meant by geosynchronous orbit, right? These satellites stay above one spot on the Earth permanently, which again, I think is what some of you are getting at with your definitions there. Okay, the last part, I need to fix that there, of chapter 5.12 is all about what's called escape speed. That's what they call it. I prefer using the term escape velocity because we have to take direction into account as well, that we are leaving the planet. And it's exactly what it sounds like. It's the speed needed to escape the gravity of a planet or a star. Earth, a satellite has to be launched straight up at exactly 11.2 kilometers per second or faster in order to leave Earth's orbit. So that is a projectile that would go up and would never come back down. It would just continue to move away from our planet. It has escaped Earth's gravitational pull. However, escaping Earth isn't the only thing that has to be done by a lot of satellites because the sun is also acting on Earth and is acting on anything that comes off of Earth. And it's actually so strong that any projectile to escape our solar system, to get away from the sun, has to be going at about 42.5 kilometers per second or faster. And we've actually done this. So NASA has launched a satellite that has now left our solar system. It's called the Pioneer 10. It was launched in 1972, which is crazy to think. And they sort of did a couple of those little slingshot things that we were talking about. They circled it around Mars. I think in 1984 it passed Mars, and then they swung it around Jupiter, and it was Jupiter's gravity that really kind of threw it out into space. And it is now in interstellar space, just floating around. I don't think they've lost communication with it, and so it'll either crash into something, or who knows, maybe some other life forms will find it. It's got like a whole record apparently of human history and different things on it, which is kind of crazy. And so, as you can imagine, escape velocity depends on the gravitational force being exerted by, a planet or a star. And as you guys know from the math, ignoring distance, mass is what makes a big contribution. So it's no surprise that something like the sun, which has an absolutely enormous mass, has a very strong required escape velocity, right? 42.2 kilometers per second. It's one of, not the highest, but up there, right? Earth, again, that's kind of our reference point, is 11.2. And then not surprising, something like the moon, which is pretty small, has pretty low, right? 2.4 kilometers per second to get off the surface of the moon. So if you think about astronauts when they went and visited the moon, it was much harder to get off of Earth and fly towards the moon than it was to get off the surface of the moon and return back to Earth, because it's a smaller celestial body and it's not exerting as much gravitational force. So in summary, I know that was like a lot of numbers I just threw you guys, but the point is that you kind of have, depending on the horizontal velocity that is applied, you can have a couple different situations that occur. Again, the minimum is 8 kilometers per second to get that circular orbit around Earth's surface, to never actually hit the ground. It matches Earth's rotation. If it's slightly more than 8 kilometers per second, they don't show that here, but you still get rotation around the Earth. It's just going to be in that elliptical shape, where it's going to sort of swing farther out and then come back. 11.2 kilometers per second, that's escape velocity. So something's fired there, you can see it right here. That is just going to go off into space away from Earth, never going to come back to Earth unless something swings it back towards us. But that's still under the influence of the sun's gravitational pull. So even though it gets away from Earth, it might just fall into its own orbit around the sun unless it's going or speeds up to 42.5 kilometers per second. Then it could leave our solar system, go all the way past Pluto, past everything, and get out of the sun's gravitational influence. And that is it for chapter 5. So, any questions on that? Okay. And again, you'll do a little reading, and this time we'll have a little like reading quiz the next time we meet to review that. All right. So then the final thing that I wanted to do today, I want to use the remainder of class time to get you going on your Rube Goldberg projects and sort of hopefully get you away from your computers for at least a little while. Not everybody has submitted the pictures of the materials yet, but everything is there on Canvas. So if you go into Canvas, let's see. I want us to come back at 1:10. That gives us a good amount of time, at least 20 minutes, to at least start putting a machine together. So there's a Flipgrid assignment that you'll be contributing to. And again, this will roll into homework, so you don't have to get it done now, but I do encourage you to get started. But on Flipgrid, I've created what's called the Simple Rube Goldberg Machine. And I'd like you to put one together using at least 4 or 5 different household items that interact in at least 3 different ways. I posted my example video that I made before we went on spring long weekend, where I got my daughter's rocking chair to rock her little toy owl to sleep, but it could be any simple task that's achieved by your machine. And some of the materials that I saw posted look great. A lot of you seem to have hardcover books. You've got DVDs. You've got athletic equipment, balls you can use. So this is your chance to sort of play around and see if you can put together a simple machine on the floor or on a table, and then just make a quick video of it. And just like my video, when you think you're ready, and again, this might take multiple attempts. So I want your machine to go all the way to the end. It's okay if you have to like help it out once or twice, but make sure that it does finally achieve its final task, right? So it's okay if you got to take multiple videos, be ready for that. You might have to delete a video if it didn't work and try again. Take some time at the start of your video to explain what should happen, right? So show the whole machine, here's each step and here's what should happen, and then activate it and see if it'll actually go through. So just like the video that I posted, that's how I went about doing it. The one piece of advice that I will send you off with is keep it simple, right? Don't try to go crazy and elaborate and have a projectile fired from halfway across the room, because stuff like that's going to be hard to do. So keep it simple. And also, I learned when I was doing this that everything has to be pretty much on a hairpin trigger, right? That if you've got things that are going to fall over, your first item has to be already pretty wobbly, right? Or is like almost ready to fall. Everything's got to be like ready to go, and then you just activate it and it sort of cascades down. So I'll be here listening if you need help, if you have questions about items or whatever, but then I'm going to give you the next 20 minutes or so to just gather your materials, see if you can test fire a few things, and if you feel ready, go ahead and film it. But we're going to meet here again on Zoom at 1:10. So in 20 minutes at 1:10, we'll come back together and we'll just chat about what happened, and that'll be it. Got it? All right, I'll be here listening if you got questions. Go for it.
Shade, I have a question.
Yeah.
I'm not at.
Hit it.
Yeah.
All right, everybody, time's 1:10. Let's come back together.
I wasn't able to finish it, if that's okay.
Oh yeah, no, that's all right. This will roll over into homework. So I don't expect that. But did anyone get close? Anyone try anything?
I was just kind of messing around.
Yeah.
Yeah.
Yeah, you'll kind of get ideas, but that's kind of the point of this, is just to think about, the way I went about it when I was doing it was I had a bunch of items. I was like, okay, I can make these fall over. I can make this like wire retract. I can do this, that. And then the trick was to try to figure out how to connect them. Like, how do I get a book to activate the wire thing? And so, it requires a little bit of finagling, but that's kind of the point. So again, this is more just for fun. But yes, so this will roll into your homework then for Monday. If not sooner, try to have a video posted to the Flipgrid. And then another part of the assignment is to then go watch a few of each other's videos and leave a little positive comment or something. Give each other some feedback. Could be interesting to do. So beyond that, the only other homework for the weekend is just to read the last part of Hewitt, chapter 5.12. And there's no reading questions this time, or reading check questions. Just take some notes and be ready for a short little do now reading quiz that we'll do at the start of class on Monday. So that's it. Just try to post a machine and do the reading and take some notes that you can, again, it'll be an open notes quiz like they always are. So, all right, that is it for me otherwise. So thank you very much. Have a good day. I will hang around here if you've got questions or anything else you want to talk about, but otherwise you're good. Thanks, kids. Enjoy the weekend.
Bye. Thank you.
Bye.
Thank you.